Okay guys, we're going to be going through chapter 7, review questions. This is in the practice textbook. Okay. Yeah, so let's just get going. Let's look at review question 7.1, the effects of interactions. Okay, so a pool ball collides head-on elastically with a second pool ball initially at rest. Do any of these properties of the system made up of the two balls change during the interaction? Okay, so we've got a pool ball, another pool ball, and this one is moving at some velocity. This one is at rest. Then they, let's draw it here. They collide. Okay, and then they probably start moving again like that, right? So moving at rest, they collide, there's an interaction, and then they start moving. Okay, do any of these properties of the system properties of the two balls change during the interaction? Momentum. Does the system momentum change during the interaction? Does the system kinetic energy change during the interaction? And does the sum of all forms of energy change in the system? Okay, so I want you to think about it. Now the answer is in the back, but the idea is that you would try and figure it out, work it out, and then we can look at the solution. Alright, so I'm so glad that you paused the video and you went and tried it. I know you did that. Okay. So what happens during an interaction in terms of the momentum? So this is from figure 7.2. So here we have exactly the same idea. You've got a cart colliding, interacting with a cart at rest. Cart 1's momentum is, inertia is half that of cart 2. And anyways, this is from earlier chapters. You know what this is. These are the velocities of the two carts. But during the interaction, we need to see something that, well, for momentum, we can see that the total momentum, this is the system momentum, okay? System. All right. So here's the momentum of cart 1. Remember, it started at zero velocity, and cart 2 started at a positive velocity, and they interacted. You can see that grayish bluish area. They interacted, and cart 1's momentum increased and cart 2's momentum decreased. But the important thing here is, if you add up the momenta as you go, if you add up these two momenta, you get this momenta. If you add up these two, you get that, and you keep adding up the momenta, you get the momentum of the system. And you can see that it remains constant throughout the interaction. That is, if it's an isolated system, right? Remember, isolated means that there's no external interactions. Okay, so have you got that? The momentum of a two-cart system remains constant. Even during the interaction, it remains constant. But let's have a look at what happens to the kinetic energy. The kinetic energy, can you see that it dips during the interaction? Okay? And this is because, remember that for an elastic collision, we said that the relative velocity, let me just move this guy down. Let me just move this guy down a bit. The relative velocity before collision and after collision is the same. Remember, for an elastic collision, the relative velocity would be the same, if you recall. But during the actual interaction, there is a point where those two, what are they called? Pool balls. They have a zero. Their relative velocity is zero. Okay? So when their relative velocity is zero, that means that their kinetic energy has dipped. But what has increased is your potential energy has increased during this time. The kinetic energy dips, okay, when the relative velocity is 0, and as that dips, your potential energy increases, and then that potential energy that was stored in this interaction gets released again into kinetic energy, so that the relative velocities after are the same, and the system kinetic energy is the same after the interaction. Okay, so the answer is the momentum remains constant, but the kinetic energy dips briefly as some or all of it is converted to internal energy, potential energy, internal energy. Right, there could be heat there as well, but I think the main thing we can look at is potential energy during the collision. Okay. Now the thing is this. So maybe to be absolutely accurate, the kinetic energy we can say is converted to internal energy. Let's be much more accurate. Internal energy, of which some of that is potential energy. Okay. Now the total energy of the system. This graph here is only looking at kinetic energy, how it dips during this interaction, and during this dip, there's an increase of internal energy. Okay, but the total system energy remains constant. Right? The total system energy remains constant. All right. Cheers.